generalization ability of statistical models, and like this trade-off between, okay, you can have something with more parameters, that in turn affects the BC invention, and then you might be able to learn more functions, but as a consequence of that, you might have slightly higher like sample complexity, and like your generalization bounds depend on like the classes of functions that you can represent. But there's the other part of this puzzle, which is how do you choose the function within your hypothesis class, and if you have an optimization algorithm, which functions does it tend to learn and would result in something that classifies even the training data points correctly. And so I'd like to talk about this optimization aspect that has gotten a lot of attention in the past few years. This is based on, coincidentally, a recent paper which has the same title, but so I'll be using some results from there, but I hope that I can like more generally talk about why overparameterization is so important, and why deep learning models rely on it, and like what advantages it offers. So just like as a brief overview of what I mean by overparameterization. So you might have like heard about like large language models or other types of deep learning models that have tons of parameters, and so they're sometimes described as overparameterized, and that means that they have more parameters than they have training data points. So if you just like do like a sort of dimension counting, if you have a model with like 10 parameters and only 8 data points, you might expect, okay, there are many ways to classify the data points correctly. So yeah, once there are enough parameters in the model, it can perfectly fit any choice of training data, and so you can get something with zero loss. Well, even though you can reach something with zero loss, it's not obvious that gradient descent will converge to it, because neural networks can be parameterized in really complicated ways, and so when you train them with gradient descent, you have this kind of non-convex objective function, and it's not clear why you should converge to a global minimum. You could have something that converges to a local minimum. But what I'd like to convince you of is that if you have a model with a lot of parameters, that makes the loss landscape favorable. And so if you draw a picture of the loss landscape, you have a lot of global minima, and not that many spurious local minima. And I'll elaborate on all of this throughout the talk.
I have a question.
Mm-hmm.
Is it favorable to want to converge to a model that has zero loss on the training data?
That's an excellent question. So I won't go too much into detail on that, but yeah, so that relates to the generalization ability of deep learning models. And yeah, so sometimes you want to converge to something with zero training loss. Sometimes you might want to do like an early stopping. So before you hit like too much of you might want to stop training after a certain number of epochs. And by epochs, I mean you do a certain number of training iterations and then you stop early, and you want to do that so that you don't overfit to the training data. But in practice, like one of the successes of deep learning is that it's able to fit the training data while still generalizing well. And some people study that in like the form of like benign overfitting and double descent and things like that. But for now, I'm just going to focus on the question of fitting the training data. Okay, so let me just describe the types of models that we're going to consider. So I'm going to write it as a function f that takes, you have parameters and you have data points. So the Rm stands for your space of parameters. Your Rd stands for your space of input data. So your model takes in a data point, and it takes in a parameter, and it outputs a number. So I write it as like f of theta x. Some people might prefer to write it as like f subscript theta of x. Like f theta is the given function, and it takes an input data point and it spits out an output data point. But I'm going to write it in this notation. And I'm also going to like overload notation a little bit. And well, if you have a single data point little x, you can write f theta of x, f of theta x is equal to little y. But you can also put in an entire data set and write out the evaluation of the function at each data point. And I talked yesterday about the hinge loss. Today we're going to talk about the square loss. And the way you evaluate the square loss of a function is you take the predicted value and you subtract it from the actual value and you square it, and that's given by the square loss. Here I just do a 1/2 as a normalizing constant, but that's not too important here. And we're using square loss just because, well, you can use that for like regression tests, whereas hinge loss or logistic loss would be more fitting for like classification tests. Okay, so we want to try to understand optimization with the square loss. And in order to understand optimization, like a good place to start is what can we say about the gradient and when is the gradient equal to 0? So we can do like a kind of simple calculation here. So we set the gradient of the loss equal to 0. Since we're using the square loss, it's like a bunch of stuff squared. So you take the derivative of something squared, you get the thing times its gradient. So you write that down and you get this kind of dot product here. So we end up getting the gradient of f times this residual, dot product with the residual is equal to 0. And you can use this as the source of a lot of the intuition about critical points of the square loss. So if you have like an equation ax equals 0, where a is a matrix and x is a vector, then there are two ways that it could equal 0, right? Either the rank of a could drop, or the residual could equal 0. Now, what happens when this residual is equal to 0? Well, that means that f theta x is equal to y. That means that your model perfectly fits the training data. For every data point x, f theta of x is equal to y. So that's the ideal scenario. So this residual is equal to 0. We want this residual to equal 0, and that happens whenever this Jacobian is full rank. If the Jacobian is full rank, then this equation equals 0 implies that the vector itself is 0. This all makes sense? Okay. So if we want to understand, if we want every local minimum to be global minimum, then it's important for this Jacobian of f to be full rank, and that's what I'm trying to convince you of here. So from now on, when trying to say the loss landscape is favorable, I'm going to basically interpret that as the Jacobian of your parameterization map is as rank n. And, well, we can also try to understand the dynamics more directly by writing down the equation for gradient descent. So let's say that we have a model that's parameterized by theta, and like we said yesterday, you can write down the equation for gradient descent as you take theta of t plus 1, and you take the gradient step. So if you do minus the gradient, then that's going to encourage your loss to decrease. So you take a step size with some coefficient eta. And a common strategy that people use to understand gradient descent when your step size is small is you take an infinitesimal limit. So as eta goes to 0, this becomes approximated by gradient flow, which is instead of doing like a discrete dynamical system, you go to the continuous limit. So continuous limit here, you can think of this as like an Euler approximation of an ODE, if you prefer to think of it that way. But just thinking of it as eta is going to 0, and the limit it becomes d theta dt is equal to minus the gradient. And so we can also express the loss in terms of this. So you write down the gradient of the loss, and then because this is equal to the derivative of theta, you write that out and you get that it's the gradient of f times the residual. And so you do a couple more computations with this. So you take the residual is, you take the derivative of the residual, and you end up getting, it as the gradient of f times the derivative of theta. This is just from using the chain rule and applying it to f. And then again, we substitute in our expression for d theta dt. And in the end, what you end up getting is the change in the residual over time is given by this gradient of f transpose times gradient of f times r of t. So basically, if you write down the dynamics of the of gradient descent, what you end up getting is like r of t is equal to minus k of t times r of t. Now, I want to try to explain what this looks like in like a really simple case. So, just like pretend that this k is just like a constant thing, right? So, like, if you have r is equal to minus k times r, then where r is the residual, then what can you say about this? Well, like for example, if k is like a diagonal matrix. So, let's say that like r is equal to.
Is the r on the left the r dot?
Oh yeah. So, like if everything is in one dimension, then you end up getting like r of t is equal to minus minus r of 0 e to the r of 0 e to the minus kt. So it decreases exponentially in time if you write it this way. And if k is a diagonal matrix in higher variables, you get the same thing. Like if you have a two dimension, k is equal to like lambda 1, lambda 2, 0, 0, then you end up getting r of t, like r1 of t, r2 of t is equal to r1 of 0 to the minus lambda 1 t, r2 of 0. And so you might think from this that you can determine the dynamics of this by looking at the eigenvalues of k, and it turns out you can actually do it in that way. So basically, if you have a constant matrix k, like constant positive definite matrix k, then you can write down the dynamics of this in terms of the eigenvalues of k. And so intuitively, if the eigenvalues of k are sufficiently large, then this will decay quickly. And that's what I'm expressing here. So in this case, the matrix K is given by gradient transpose times the gradient. And that's what we write down as K of theta of t. And this matrix is a special name that people talk about a lot. It's called the neural tangent kernel. So because of what I've written down here, understanding like the eigenvalues of the neural tangent kernel is very useful in understanding the dynamics of gradient descent. Because if this matrix, if you can study its eigenvalues and show that they satisfy certain bounds, you can show that the loss decreases quickly. So basically, this is a maybe slightly more rigorous way of saying what I just said, but the idea is the exact same as what you would write down for constant matrices. So if the rank of the Jacobian is equal to n, which was the nice property that we mentioned before, then the minimum eigenvalue of k is positive because we wrote this down as the gradient transpose times the gradient. So if the matrix gradient f is full rank, then then the same will be true for this kernel matrix K, and so it'll have all of its eigenvalues will be positive. So let's just assume that that holds throughout training. Then basically by Grunwald's inequality, which basically says if you can, if an ODE satisfies an inequality, then you can compare it to the ODE that satisfies the equality. I don't want to get into the technical details of it, but basically it says that the loss satisfies the decay that you might expect from looking at the eigenvalues. So if all of the eigenvalues of the neural tangent kernel are at least lambda, then it satisfies this exponential decay that you might expect from looking at that matrix. So to summarize all of this, if we can show that the NTK is positive definite, and we can find bounds on this minimum eigenvalue lambda, then we can understand that we can show that the neural network quickly converges to zero loss. And this is a really fruitful idea that led to a lot of papers that show that that neural networks that are over-parametrized converge to zero loss. So you can get convergence proofs from this. And you need a little bit more than just knowing that the neural network at initialization has the Jacobian is full rank, because you also need to know that this K of theta of t, like its eigenvalues don't get worse throughout training. Like they might be nice to begin with, but the lambda might go to zero somewhere in the middle of training. But with some like high dimensional statistical magic, you can show that if you have enough parameterization, then the model will not move too far from its initialization. The eigenvalues won't move too far from initialization. And so everything will stay nice throughout training, and you can get convergence from that. So that was like a very quick justification for why we should care about the Jacobian of a model being full rank. Basically, it has really nice properties for in terms of optimization. If you have the Jacobian is full rank in a lot of places, then the model will quickly will have its loss quickly decay, and there will be a lot more global minima than local minima. Or I should say, a lot more global minima than spurious local minima. Any questions so far? Yeah.
Just to recall, the Jacobian being full rank means that it's like the rank is the size of the data that we're using, right? And it's like the data sets.
Yeah, it's the size of the data. So I guess to be more precise, I should say rank n. So in this case, I'm going to assume that the number of parameters of the model is always greater than the number of data points. So that means full rank is the case where this Jacobian has rank n, because n is always going to be less than the number of parameters n. Okay, so I said some generalities about over-parameterized networks, why we should care about the Jacobian having full rank. Now I'd like to specialize to a specific type of model, and that is two-layer ReLU networks. So we're going to consider a neural network with two layers. So your first layer is given by a matrix W, so you apply a matrix W to your data. And then you apply a nonlinearity sigma of x, where in this case sigma of x is the ReLU function. So if you have a positive value like 5, it maps it to itself. If you have a negative value like -5, it'll map it to 0. And this serves as a nonlinearity that you apply element-wise, so that your model itself is not just a linear mapping. And you can compute out the Jacobian of this model, and if you compute the Jacobian with respect to a row of W, you end up getting bi times sine of Wi transpose x times x. So this is basically applying the chain rule. So the derivative of the ReLU function, if you look at the derivative of max of 0 and x, then it ends up being 0. I'll just draw a picture. This is the ReLU function. And then you look at the derivative of ReLU. It ends up being 0 here and then 1 here. So it ends up being the sine of W transpose X. Some of you, I know, will hate this, but I'm using sine of X to mean 0 if it's less than 0 and 1 if it's greater than 0. And it's not minus 1 and then 1, it's 0 and then 1. And you can write this using a bunch of matrix operations, like here, you can write it as V with element-wise product with A, and here you can write down the tensor product with Xj. And so to rephrase everything, the Jacobian is full rank. Jacobian of the model is full rank when the set of vectors is linearly independent. Maybe I should very quickly describe what I mean by this tensor product. So what I mean here by tensor product is like, so if V is a vector and W is a vector, you can, this tensor product, you can think of it as, so let's say V is in Rm and W is in Rn, then by, this is a vector in Rn by n, so it's a matrix and it's equal to, you can think of it as V times W transpose. If you're more algebraically inclined, you can also think of it as an element of the actual tensor product, Rm tensor Rn, and everything will work out in the exact same way. But more concretely, you can think of it as V times W transpose. Okay, so we want to figure out when this Jacobian is actually full rank. And we saw in the last slide, this is equivalent to showing that this the set of tensors is linearly independent. And you can do a small simplification here. Instead of doing V tensor Aj, V element wise product Aj tensor Xj, you can kind of cancel out the V. The V is not really important here. And this is like you can pretty quickly prove this by writing out the definitions. So here, let's suppose that you have some linear combination of these vectors that is equal to 0, and that means, what does this mean? If you unravel this, that means that for each entry I, the ith entry of this is equal to 0. So we write it out in coordinates, and then what that means, since the VI's are non-zero, we assume that in this slide, what that means is you can cancel out the VI, and so you're just left with stuff with the entries of A and the entries of X, and that implies that this whole thing without the VI is equal to 0. Basically, all we did here is we said the entries of V are non-zero, so we can cancel it out. So what this means is we can ignore what the outer layer actually is, because it doesn't affect whether the matrix is full rank or not. Okay, so now we have taken this question about neural networks and optimization and basically turned it entirely into a linear algebra problem. And the question is, you have some set of tensors, Aj tensor Xj, and you want to know, okay, what can keep this from being full rank? When is this not rank n? Or, I guess I should say, what conditions on the Aj and Xj can keep it from being full rank? Now, there are kind of trivial conditions that will keep it from being full rank. Let's say that all of the Ajs are equal to 0. If all of the Ajs are equal to 0, then this whole set is going to be just zeros, and then it's not going to be full rank. you can kind of generalize this. You can say if there's some linear dependence in the activation patterns, then the rank is going to drop. And the same thing is true for the data points. If there's some linear dependence in your data points, then, or if the data points all lie in some low dimensional space, then the rank can drop. Now, okay, let me just quickly review what, I wrote down AJ. Let's remember that, so AJ is like the activation pattern. So this is the activation pattern of the J data point. So let's like suppose that you have some, you have some vector x, and you have a neuron. I don't know why I'm doing an arrow here. So let's say you have data point xj. And you have a bunch of neurons which you evaluate on xj. So like, let's say that like w1 xj is greater than 0, and you have another neuron which is less than 0, which is not activated on this data point. So for this, you would get the activation pattern is equal to 1 and then 0. Right? So this is how you calculate your activation patterns on each data point. Now, you might see that there's a problem here, which is that you can never prevent, there's always going to be like some value of W that's going to make the data points like evaluate to like a 0 activation pattern. And that's always going to be an issue. But let's forget about that for now. Let's pretend that all the activation patterns are nice. Then things can also go wrong in the data set itself. And yeah, if all the data points are equal to 0, then things can be bad as well. So we can at least keep the data set nice, and what we're going to do is we're going to assume that the data points are generic. What that means is, for example, let's say that if you're in R2 and you generate a bunch of random data points that are like Gaussian or uniform in a circle or something. So if you generate a bunch of random data points, what's the probability that like 3 of them lie on the same line?
It's not 0.
Yeah, it's always 0, right? Because, well, if you take a Gaussian, then you have 2 of your data points, and the probability that the Gaussian lies on a particular line, that's always equal to 0. So we're gonna use this as to make an assumption, which is that basically we want to prevent these like measure 0 events from happening. That you don't want data points which lie in some very specific configurations. So that's what we're going to assume, that basically, maybe I should speed up a little bit because this is a lot of just technical assumptions. But basically, we say that a subset is algebraic if you can define it by polynomial equations, and we say that a property holds generically if it holds for everything except for an algebraic set. Maybe like a concrete example is, like, you look at the determinant. If you take a matrix and you generate it at random, then it's not going to have determinant 0 if you do like a Gaussian matrix. Because for almost all matrices, they don't have, they don't satisfy the determinant vanishing. So basically, this is like a technical assumption that we're going to use. We're going to assume the data set doesn't have these kind of special geometric properties. You can think of it as, if you add a little bit of noise to all the data points, then they're not going to lie in these weird configurations. Okay, so I'd like to maybe describe the intuition for why networks, why the landscape is nice. So one particular case where you will get that the set of vectors is full rank is when the AJs are full rank, when the activation patterns are full rank. You can also write this down in a few lines. Like, how do you know that just because the AJs are full rank, that the tensors are maybe full rank? So you can write out each of the steps here. So you suppose that some linear combination of the tensors is equal to 0, and then you write down what does each entry of this look like. Well, you can write it as aij times xkj is the summation is equal to 0. And then what? Well, if you know that the summation is equal to 0, then because the matrix A has linearly independent rows, then that implies that each of these coefficients is equal to 0. Alpha j times xkj is equal to 0. And if this is true, then you just cancel out the xkj, and then you get alpha j is equal to 0. So what we've shown from this is like a fact that you might expect, which is that if your AJs are linearly independent, that implies that tensoring them with the XJs, it'll stay linearly independent. So basically, we have this, we want to show that the set of tensors is linearly independent. We want to see when it's linearly independent. And we have one condition for it, which is when your activation patterns are linearly independent. And we can phrase this in a combinatorial way. So we have a bunch of activation patterns which look something like this. And you have a bunch of 0, 1 matrices. So you have portions of your loss landscape which are given by activation patterns like this that depend on how each of the neurons configure with your data points. And based on whether these signs are positive or negative, you form a matrix based on that. So one of these axes might describe the neurons, and the other axis might depend on the data points. So you have a bunch of data points and a bunch of neurons, and you want to enumerate out whether the dot products are positive or negative, and that gives you an activation pattern. And we want to be able to tell when is this activation pattern full rank. And well, we can't always guarantee that it's full rank because of what we said before. If a bunch of neurons are dead, that means, like, for example, here, when you have a bunch of things that are 0, then that's when things can be bad. But we can say, the direction that we can go in is to say, okay, well, it's not always going to be good, but for most choices of activation pattern, so for most of the loss landscape, which is regions of the loss landscape are described by these activation patterns, if for most of these matrices this is full rank, then you can say that most of the loss landscape is good. So we want to understand how many matrices that are given by zeros and ones have rank n. And you can also translate this into like a probabilistic statement, which is if you choose a matrix like this at random with zeros and ones, what's the probability that it will have rank n? And so let's just try to understand that. So there are a lot of different ways that you can approach this. It's like a classical random matrix result, and one approach is to look at n by n submatrices. So if you have an n by n matrix, you can restrict it so that you just look at like a given n by n matrix, and you want to figure out, okay, what's the probability that this thing is full rank? And by this, there's a result by Bourgain and Wu and others, and this is like a series of papers. It's a very nice result that if you have an n by n square matrix with 0, 1, whose entries are selected uniformly from 0, 1, then with very high probability, this matrix is going to be invertible. This is, you can so they, this is actually a very non-trivial result for square matrices. But if you assume that it's like an n by 2n matrix, then you can prove this in like a slightly more elementary way using some concentration inequalities. But you can obtain a better result by working a lot harder. And fortunately, we don't have to work hard. We can just invoke this result. So applying it to our setting, we suppose that like m is larger than n, and you take a random activation matrix. Then from this, we can say that the probability that the determinant of A is equal to 0 decays exponentially as n increases. So if you have a lot of data points, or even like a moderate amount of data points, this decreases very quickly. So for most matrices, this determinant is going to be full rank.
Where did the 0.72 come from?
Oh, that's an excellent question. What's 1 over square root of 2? I think that's close to 0.72.
Okay.
Wait, yeah, I think so.
Yes.
Is it 0.71? Okay, great.
Yeah.
Yeah.
So I mean, how do we know that the activation pattern is actually IID uniform?
Oh yes, that's a great point. Well, we don't know that the activation pattern is IID. I mean, we don't know that it's IID uniform. There are some cases where you can make it more likely. So if your data set is very high dimensional, then there is less correlation between your data points, and so you get IID more often. But we don't need it to actually have that probability distribution, but rather we're trying to understand how many regions. It's like a combinatorial result. Like how many regions are you going to have in which this thing is full rank? So then we can say that in most of the loss landscape, this is the Jacobian has full rank. So we're using probability to prove a combinatorial statement.
So you are more interested just like the volume of the, like how much is how big is the proportion of the volume in that probability space, but you are actually not using the IID to prove things. Right? It's more like a deterministic problem.
Yeah, it's a deterministic problem. So if you wanted to like have a more fine-grained understanding of the volumes of the good regions, like it could be that there are a lot of good regions, but they just have really small volume, and the bad regions have really big volume. Then you would have to go beyond this IID setting. But if you want to enumerate out how many good regions versus how many bad regions there are, then this works just fine for that.
To get to the corollary, can you do something like this to union bound over the like kind of minors, the square minors in a Wadding matrix? Is that how they go from theorem to theorem, or is it more complicated than that?
So it's even easier than that. Which is you just take so you have this tall matrix, and you just take the first thing, because the good events are that one of the minors is as full rank. So you just take the first one, and then you'll get this value just from that. Okay, so then from there, I basically told you the proof that we use this corollary to count the fraction of activation regions which are good, and so you have some epsilon that you want to describe as the probability of there being a bad region, or like the fraction of bad regions. You phrase it combinatorially. So by what we've just said, if you have more parameters than data points, and the number of data points is larger than some threshold log 1 over epsilon, then all but a fraction epsilon of regions are going to be full rank. And this is more parameterization than we'd like, because remember, you have your matrix matrix W. You have a matrix W, that's basically all your parameters. And that's in R to the n by d. So you actually have m times d parameters. So here we're requiring m to be larger than n. That's what we, well, so that's the condition that we needed to get this linear independence thing. But then the number of parameters is m times d, which is larger than or equal to n times d. So that's a lot of parameterization. So you have n data points, but n times d parameters, which might be fine, or it might be too much. Like if you have a really high dimensional data, then this could be a lot more than the number of data points. But it turns out you can use a similar proof strategy to the one that we used, and you can use the higher input dimension in your favor, and basically split up the data set. And the way you split up the data set is if the dimension is d, then you can split it into d clusters, and from that you can get this bound that if m is larger than n over d, and it's also larger than a quantity that this omega of n over epsilon d, then this holds that in all but a fraction epsilon of the activation regions, the Jacobian is going to have full rank. Yeah, I have some other things that I could say, but I think we're supposed to stop at